بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 9 في Digital Signal Processing DSP. اليوم في عندنا بعض الإشيوز أو بعض الأمور اللي بنحب إنه نبحثها مع بعض إحنا وياكم regarding the impulse response. الموضوع الأول إنه هو stability condition in terms of the impulse response. يعني شو الكونديشن على الامبلس ريسبونس حتى نقول انه السيستم ستيبل ولا لا. نتذكر احنا وياكم recall the Bible stability criteria اللي بتحكي انه for every bounded input i.e. magnitude of x of n less than or equal some beta x less than infinity. This is for all n. This implies the output is bounded. بمعنى آخر the absolute value of y of n less than or equal beta y less than infinity for all n. So this is the Bible stability criterion. For every bounded input, the output is also bounded. Okay, let's put y of n here in terms of the linear time invariant system, which says that y of n is the convolution of h of n with x of n minus k. And this is h of k. h of k, x of n minus k, this is from k equals minus infinity to infinity. Okay, so this is the equation that we have last time. And let's check the stability here. I'm going to take the absolute value. So I'm going to take the absolute value for both. Now, if I am going to take the absolute inside the summation, then we have inequality like this. So you have summation from k equals minus infinity to infinity, absolute value of h of k times the absolute value of x of n minus k. Okay? And this is reasonable actually. Now, x of n minus k, this is summation from k minus infinity to infinity. This means that we are taking all the values of x. So this one here is also less than or equal. We're going to substitute for x of k the maximum value of x. So this summation definitely is less than the summation of h of k times beta x from k equals minus infinity to infinity. So we substituted the maximum value of beta x, which is the upper bound of beta x, instead of the absolute value of x of n minus k. So definitely this one is greater than this one, because we have beta x is greater than all the values of x of n. Okay, this one is constant. I'm going to take it outside. So take it from here and put it here outside the summation. Okay, all right. Let me just organize things. Okay, I'm going to let it here. So this one here is equals to summation, beta x times the summation of the absolute value of the impulse response from k equals minus infinity to infinity. Okay, so by the end, we end up with that y of n absolute is less than this value. Okay, now for this value to be a constant, and we call it beta y, this summation should be summation of h of n from h of k from k equals minus infinity to infinity should equal some s less than infinity. So if this one has a summation less than infinity, then this is absolutely summable, which means that for the system to be bibostable and the absolute values, the summation of the absolutes equals to s less than infinity, which means that finite value this means that the impulse response should be absolutely summable. Okay, so for stability condition, in terms of the impulse response should be absolutely summable. So if you want to check for bibostability, check whether the impulse response is absolutely summable or not. So if this one equals to s less than infinity, then this means that your system is bibostable. Bibostable system. If the impulse response is absolutely summable, then the system is bibostable. Okay? Okay. We'll see this in a while by an example, but let me see the other thing that we need to check, which is the causality in terms of the impulse response. Causality condition in terms of impulse response. So the causality condition in terms of the impulse response. Okay, remember that, or recall that y of n is equal to the summation from k equals minus infinity to infinity, h of k, x of n minus k. This is for LTI system. Okay. Now, I'm going to divide this y of n into two parts. The first part is the summation from k equals minus infinity up to minus 1, h of k, x of n minus k. And the second part is the summation from k equals 0 up to infinity, h of k, x of n minus k. So we have two summations. And now I'm gonna take the elements inside the summation and see what will happen. Those will go like this, from minus infinity up to minus 1. So we will have, if we come from minus infinity up to, let's say, minus 3, then you have h of minus 3, x of n minus minus 3, so this is plus 3, plus h of minus 2, x of n plus 2, plus h of minus 1 x of n plus 1, and this is the n. So all the values here are x of n plus 4, x of n plus 5, and so on. So those are the summation, or the elements inside the summation, the first summation. In the second summation, we will have, starting from 0, then you have h of 0, x of 0, plus h of 1, x of n, sorry, h of 0, x of n. I'm sorry about this. H of 0, x of n minus 0, so it's x of n. This one, h of 1, x of n minus 1, plus h of 2, x of n minus 2, plus h of 3, x of n minus 3, and it goes up to infinity. Okay? Looking at the first part and the second part, and remembering that when we say a causal system has to satisfy the following. We know that for sure that a causal system y of n is a transformation of x of n, x of n minus 1, x of n minus 2, and so on. So it's a function of the present and previous instance of time, but not the future instance of time. Now, looking at those are future values. Future values, those are values of x of n. But here, those are present and previous values of x of n. So this term here should be 0. And for this term to be zeros, we have to have, so for causality, we have to have h of k, which are those values, to be zeros. This one to be 0, this one to be 0, and this one to be 0, and so on. So h of k should be equal to 0 for k less than 0. For k less than 0. Okay, one more interpretation for this is that we have, if you have a delta of n as input to a system, then the output is h of n. Okay? Which means that you are applying delta at n equals 0. This is your delta of n, which is equal to 1, and it's zeros otherwise. Now, if we apply x of n equals delta of n at n equals 0, then for a causal system, y of n should have values for n equals 0 and above. I mean 0, 1, 2, 3, and so on. So you don't have to have For a causal system, we don't have to have an output before you apply an input. No output before you apply an input. This statement should always be when you have a system that is causal. Okay, before we are going to take an example, but before we do that, let's take one mathematical tool that we need in our analysis, and that is, let's discuss the geometric series. The geometric series is a series that has the form S equals to summation from n equals 0 up to capital N alpha to the power n. So this is what we call a geometric series. Now, we're gonna discuss how can we find the whole summation, how we can find a formula, compact formula for S. We need to find a compact formula for S. Okay? Now, I'm gonna do this. I'm gonna take S sub n, which is equal to the summation from n equals 0 up to n, alpha to the n, and this is equals to 1 plus alpha squared plus alpha cube plus alpha to the power n minus 1 plus alpha to the power n. Okay, so this is the summation of geometric series for alpha to the n. Let's take S to the n sub n plus 1. So we will increase this n by 1. So we will have summation from n equals 0 up to n plus 1, alpha to the n. This equals to 1 plus alpha squared plus alpha to the n minus 1 plus alpha to the n plus alpha to the power n plus 1. Okay? So we took summation sub n, which the last power or the maximum power here is up to the n, and the next one is n plus 1. Okay. Let's see how can we deal with that. First of all, I'm gonna put some Sn plus 1 is equal to, notice that here, this one is S sub n. So this one is S sub n plus alpha to the power n plus 1. So from 1 to n, it's the same as this one. So this one is Sn. So Sn plus 1 is equal to Sn plus alpha to the n plus 1. Okay, take also S sub n plus 1 equals to, I'm going to take 1 plus alpha, and we take some common factor, alpha. So if I'm going to take this one here, I'm going to take alpha common. So the first one will be 1 plus alpha squared plus, and the last one here is take alpha common, so this one is alpha to the n. This one here in the square brackets is also S sub n. So we have S sub n plus 1 plus alpha S sub n. Now, S sub n plus 1 is also equal to Sn plus alpha to the power n plus 1. Okay? We will cancel this one now. We take those two, take Sn as a common, 1 minus alpha equals to 1 minus alpha to the n plus 1. Then S sub n is equal 1 minus alpha to the power n plus 1 over 1 minus alpha. So this is our formula as a compact formula for the sum. So if you are summing to Sn, then this summation here is equal to 1 minus alpha to the n plus 1 over 1 minus alpha. Okay? Please remember this. Now, as n approaches infinity, so if you are taking n as infinity, then we have two cases. Case number one, Sn converges and has the sum equals 1 over 1 minus alpha if magnitude of alpha less than 1. 2, Sn diverges if the magnitude of alpha is greater than or equal 1. Okay? So if you are summing S infinity, then this is 1 over 1 minus alpha, given that the magnitude of alpha is less than 1. Okay, let's take, so please remember, the geometric series is very important for us. Most of the time we are looking for n approaches infinity. And we have those two cases when n approaches infinity. But for any regular n, then whether alpha is greater than 1 or less than 1, this summation is valid. Okay? So the summation is valid always, regardless of the value of alpha. Okay. We'll take an example here. Consider an LTI discrete time system with an impulse response given by h of n equals to alpha to the n mu of n, and the magnitude of alpha is less than 1. What is required here is the system stable, is the system causal. Notice that the definition here of h of n can be written as h of n is equal to alpha to the n for n greater than or equal 0, and 0 for n less than 0. We can replace this by multiplying h of n by mu of n. So this is another way of defining alpha to the n mu of n. And here we have to make sure that the magnitude of alpha is less than 1. Okay? All right. So to check for the stability we have to make sure that h of n is absolutely summable. The impulse response should be absolutely summable. Okay? We will check that. So S, which is equal to the summation of h of n from n equals minus infinity to infinity, and this is equal to the summation from n equal infinity to infinity, alpha to the n mu of n absolute. Now, mu of n is 1 for n greater than or equal 0, and 0 for n less than 0. So the summation can be, we can redefine the summation from n equals 0 up to infinity, the magnitude of alpha of n square to the power n, which is also can be written as alpha magnitude to the power n from n equals 0 up to infinity. Okay? So this one is the same as this one. And since the magnitude of alpha is less than 1, then S is equal to 1 over 1 minus magnitude of alpha. Okay? And the system is stable. Okay. Is the system causal? Causality. The system is causal since h of n is equal 0 for n less than 0. So you have causal. So we have a causal system. Okay? Okay. Okay, let's move to another issue regarding the impulse response. And we'll see the connection between systems. So we'll study cascade and parallel connection of LTI systems. So we'll see what is a cascaded system, what is a parallel system. Take a cascade system. Cascade system means that the first system is an input to a second system. So you have two systems in a row. This is h1 of n, h2 of n, x of n, and this is our y of n. So this is what we call a cascade system. Okay. The output of the first one is the input to the second one. Okay, in such a system, the whole h of n of both of them is the convolution of h1 of n convolved with h2 of n. As practice for you, prove this formula or this result. Please prove it make sure that you understand that h of n is the convolution of those two. You can do this by saying that this one here is, let's say, y1 of n, and y1 of n is the convolution of x with h1. y1 of n is the input to this one, so y is the convolution of y1 with h2, and then replace y1 with its formula in terms of x and h, mix them together, and you will find out the solution. But do it yourself as an exercise. Okay. Now the parallel connection. Here the systems are in parallel. You have h1 of n, and you have another system parallel to it, h2 of n. Both have exactly the same input, x of n going inside. Those two outputs will be added together, and you have y of n. And notice here that your h of n this is a parallel connection, for h of n is equal to h1 of n plus h2 of n. Okay? So the cascaded, it's the convolution, the parallel connection, it's the addition. And again here, as practice, prove this result. You can look at this as this one x convolved with h plus x convolved with h2. They are added together equals y. So you can take x outside the convolution, and you can say h1 plus h2 convolved with x equals y. So the proof is very easy. Okay, so this is what we call a parallel connection. This is what we call a cascaded connection. You can have so many cascaded stages, actually. You can have y1, y2, sorry, h1, h2, h3, h4, all of them cascaded, so you do the convolution in a row. Okay? Sorry. I'm going to take an example and see how we are going to solve this. Let me take the following example. We have a system that has y of n. This is h1 of n, h2 of n, h3 of n, h4 of n, and we have here x of n. You see, so the whole thing here looks like one h. What is this h? You know, inside this box you have x of n going to certain h, and you get y. So our h of n here is equal to, notice that here you have h1 directly related between x and y, so this is our h1 of n plus you have H2 cascaded with the summation of those two and goes to the addition and added to I. So this one is convolved with the addition of those two. So this is H2 of N convolved with the summation of H3 of N plus H4 of N. Okay? As you can see here, X related to H1 directly between X and Y. So H is H1. And you have here parallel to it the whole thing. But this one, H2, is cascaded with the summation of those two. Okay? So those two can be added together as one H cascaded with H2, added together with H1. So you have summation H1 plus H2 of N cascaded with the summation of H3 and H4. Okay, just to distribute the convolution over the summation, H1 of N plus H2 of N convolved with H3 of N plus H2 of N convolved with H4 of N. So this is our total H of N. Now, to continue the problem, let's make it more practical, and we will assume that, or given that, H1 of N is equal to delta of N plus 1/2 delta of N minus 1. Graphically, this is 1, N equals 0, 1, and at 1 you have 1/2 at N equals 2. So this is N, and you have 0 and 1. So H1 of N is this. H2 of N is equal to 1/2 delta of N minus 1/4 delta of N minus 1. H3 of N is equal to 2 delta of N, and H4 of N is equal to minus 2 1/2 to the power N mu of N. Okay? Okay. We will evaluate, first of all, this convolution and this convolution. But before we do that, recall that X of N convolved with a delta is equal to X of N. Okay? And any X of N convolved with a shifted delta, this is also equals to a shifted X of N at the same delta, where the delta, at the same location of the delta. So those are very easy to show. You can do that taking any X and convolve it with a delta, and you will end up with X of N itself. Okay. So we will evaluate H of N term by term. So we will take H2 of N convolve with H3 of N, and this is equals to 1/2 delta of N minus 1/4 delta of N minus 1 convolve with 2 delta of N, which is H3, 2 delta of n. Now, this is equals to delta. We assume this one is x, this is a delta, so 2 times 1/2 is 1 delta of n. The function x, where the delta is, and the second one is 2 times 1/4, it's 1/2 minus 1/2, and it should be delta of n minus 1. So this is delta of n minus 1/2 delta of n minus 1. Okay. The second term, or the third term on our h of n that was below here, is h2 of n convolved with h4 of n, which is equal to 1/2 delta of n minus 1/4 delta of n minus 1 convolved with minus 2 1/2 to the power n mu of n, and this is equals to minus 2 times 1/2, it's minus 1/2 to the power n mu of n. So it's the function at the delta, which is at n. And the second one is minus 2 times 1/4, it's plus 1/2 times 1/2 to the power n minus 1, because the delta is n minus 1, mu of n minus 1. Okay? 1/2 here with this one, so this is 1/2 to the power 1, and you have to the power n minus 1. So we say that this is minus 1/2 to the power n mu of n plus 1/2 to the power n mu of n minus 1. I'm going to take 1/2 common, 1/2 to the power n, so we end up with minus mu of n plus mu of n minus 1. This one here is minus delta of n. Minus mu of n is ones with negative minus ones from 0 up to infinity. This one of ones from 1 up to infinity, the addition is 1 delta with negative sign located at 0. Okay, so the answer here is minus 1/2 to the power n delta of n. Okay, let's stop here. The delta here is at 0. So n, the only non-zero value for this delta to be 1 is at n equals 0. So this is equals to minus 1/2 to the power 0 delta of n, and this is equals minus delta of n. Okay, minus, because the delta is only located, the only non-zero value for delta is at n equals 0. So this is 1/2 to the power 0, which is equal to 1 with a minus sign. So it's minus delta. So our last step here is just to sum the values. H of n is equal to h1, which is the delta of n plus 1/2 delta of n minus 1. So this is our h1 of n, plus this item here, which is plus delta of n minus 1/2 delta of n minus 1, okay, plus the last term, which is minus delta. Okay, so this one here is h2 of n convolved with h3 of n, and this one here is h2 of n convolved with h4 of n. Okay, now look at this. You have minus delta at minus 1, minus 1/2 plus 1/2. You have minus delta here with this one. So this one cancels with this one. So I'm gonna put here, sorry. So this one with this one, this one with this one, and h of n is equal to delta of n. Okay? So this is our final answer. H of n is equal to delta of n. Okay, these were some issues regarding the impulse response for linear time invariant systems. I hope that you will find this lecture interesting. Thank you very much, and we'll see you in the next lecture. Thanks.